Calc. Here we are. All right, you guys. Hey, I like doing the Riemann sums with you both in class, and then we tried to finish up today in some of my classes. Some we did, some we didn't. So I'm just going to finish off this last problem here for the notes. So we were here, okay? We were just looking at this, all right? And there's three theorems you guys are responsible for. And to help you sort them out, intermediate, I think of IN is in between, right? In between. You use this when you're talking about a continuous function. Doesn't have to be differentiable. It just has to be continuous, okay? On an interval from A to B. And f of A would be here, f of B would be over there. And what it's saying is if you pick any value n in between f of A and f of B, it's got to hit somewhere on that curve. Doesn't say where, doesn't say how to find where. Sorry, my eyes are itchy. It just says that it exists, okay? That's the intermediate value theorem, okay? All right, and they call that value C. One of these values where it hits, they'll call that C, okay? And so f of C equals n, that's what it's saying. Okay, mean value theorem, MVT, often abbreviated MVT. Think of M for slope, okay? The mean value theorem says the instantaneous rate of change equals the average rate of change. That's what it says. But it does need to be differentiable, okay? So this curve would not work for the mean value theorem necessarily because the problem is that you have an undefined slope here at several different points on the curve. Okay, and then Rolle's theorem is kind of a repeat of this. It's a special case of the mean value theorem. And what it says is if the function begins and ends at the same y value, okay, and you have a differentiable function in there, what it's saying is there's got to be a place C on that curve, at least one place C where the derivative is zero, okay? So this is a typical question for BC Calc. It says, is there time between 1 and 6 when the rate of change of the rate is equal to a particular value, okay? And so let's look at this picture of the graph here, okay? So they want to know, is there a point between 1 and 6 where the rate of change of this graph, even though we don't know anything about this graph other than the fact that it goes through 1, 240 and 6, 150, and that the fact that the graph is decreasing, okay? There are all kinds of ways that you could draw a graph decreasing through those points there, okay? There's all kinds of ways on this interval from 1 to 6, okay? And so one typical way of handling this is to take a look at the time and R of t. Let's just look at the data at 1 and at 6, okay? At 1, it was 240 gallons per hour. And at 6, I'm just copying the original data in the chart, it was 150 gallons per hour, okay? And so my first inclination here is to see, well, what's the average rate of change over that interval, okay? So that would be the difference between these. The average rate of change on this interval from 1 to 6 would be, I do y2 minus y1, so 150 gallons per hour minus 240 gallons per hour over 6 minus 1 hours, okay? 6 doesn't wasn't units of hours, okay? So this is what? Negative 90 gallons per hour over 5 hours, okay? And that's negative, oh, look at that. It's negative 18 gallons per hour squared. So negative 18 gallons per hour, all right? So let's look back and see if this function meets the hypothesis of the mean value theorem, okay? It says it's continuous and differentiable. Well, what did it say about this function? It said it has 1,000 gallons of oil, and it said that it's differentiable. So right there, if it's differentiable, it must be continuous. To be quite honest with you, the number of gallons in a tank of number of gallons of oil in a tank really can't like magically change. Okay, it's got to be continuous. Okay, so it's differentiable, and It is continuous, and so we are good to go here. If it's continuous and differentiable, what's kind of funny about that is if you just say it's differentiable, that takes care of both cases, okay? Then it says there is at least one point on this interval where the derivative does in fact equal the average rate of change. So even though I can't tell you where that point is, that we don't know, because R of t is continuous on 1/6 and differentiable. Okay, it's differentiable from 0 to 10. But to meet the hypothesis of this, it's differentiable on the open interval 1/6. Then by the MBT, there must be at least one point, and we call that C, at least one point or time when R prime of t equals negative 18. Oh gosh, I just barely can squeeze this in here. Gallons per hour per hour. Okay, the mean value theorem guarantees it. Okay, the intermediate value theorem between 1 and 6. What that would guarantee us is that somewhere the rate is between 240 and 150. Okay, so if they say, is there a time when R of t equals 200, you would say, 200 gallons an hour. You would say absolutely, by the intermediate value theorem, there must be at least one point where it's 200, okay, gallons an hour. All right, but this is about the second derivative. So we have to take the derivative of the derivative. We have to take the derivative of R of t. And so what we do is we look at the average rate of change between 1 and 6. Okay. And to be honest with you, they often give you problems like this where they will further break it down and they'll only have it won't match this overall interval, but it will match one of these two subintervals. They'll often make you kind of work for it. Okay. In other words, you'll have to work out this average rate of change and work out that average rate of change. And then you find out that it only matches one of those two. And so you have to say, well, since, it equaled the average rate of change over this subinterval, et cetera, et cetera, et cetera. And then you have to connect the pieces. And so they really do make you work for it sometimes. Okay. All right, you guys, it has been an absolute pleasure. Okay. Take care. Hope to see you in class. Can't wait to see you in class either next week or the next time you get to come to school. Okay. Bye-bye.